It's a pleasure to welcome Sidhanth Mohanty from MIT. Sidhanth did his PhD at UC Berkeley, and even before that, I think he was an undergrad at CMU. And he's been doing fantastic work in a lot of areas, including pseudo-randomness or high-dimensional expansion, expander graphs, and statistical inference and analysis of Markov chains, in analysis of semi-definite programming. And today he'll tell us about some of his most recent exciting works.
Yeah, thank you so much for the very kind introduction, Madhur. And thanks to all of you for coming. I'm honored to be here today to be able to tell you about some of the work I've done with my collaborators recently on a quest for an algorithmic theory for high-dimensional statistics. So let's start with a simple motivating example. Let's say there's a bunch of people. A bunch of these people are from Massachusetts, like the ones labeled blue, and a bunch of people are from Illinois. And you know who is friends with whom. But now you're given this graph, and you're supposed to guess who is from Massachusetts and who is from Illinois. And this is not just any arbitrary graph. You have some prior on what its structure looks like. For example, you know that people are likely to have more friends where they live. So let me tell you all about a stylized model that tries to capture networks like this that we see a lot in the real world. So the stylized model is called the stochastic plot model. So you have n vertices, and each vertex is assigned a color, either red or blue. And now I need to tell you how the graph is drawn. So for a pair of vertices which have the same color, you put an edge down with some probability, which here I'm calling 1 plus epsilon times b. And for pairs of vertices that have opposite colors, you put an edge down with probability 1 minus epsilon times b. So the intuitive picture you should have in your minds is two dense clusters with sparse connections in between. And now your goal is, given a graph like this, you want to estimate what the hidden coloring is. The colors have been hidden away from you. Okay, so now since you know exactly how this graph was drawn, and also exactly how the signal was drawn, to figure out the hidden coloring, a lesson from statistics is to use Bayes' rule. So if you simply use Bayes' rule, it tells you exactly what this posterior distribution of the hidden coloring given the graph is. And it turns out if you simply write down this posterior distribution and sample from it, you get an optimal algorithm. That is, you get an algorithm that estimates the maximum fraction of colors correctly. That's possible information theoretically. Okay, so while this procedure is optimal, it's completely unclear how to efficiently implement this. For instance, this distribution here is supported on 2 to the n many coloring, so it suffers from some kind of cursive dimensionality. So you can't simply write down all the colorings and enumerate over them. So the question that we'll be interested in today is, what can we do given only polynomial in n time? Okay, but this is just one example of a much broader class of problems, which I'll call high-dimensional statistical inference problems. So in one of these high-dimensional inference problems, you have a hidden signal, and then you observe some data, which comprises of noisy observations of the signal. And your goal is to extract the signal from data with an efficient algorithm. And this is a paradigm that captures a lot of well-studied tasks in high-dimensional statistics. For example, just to give you all a few hand-picked examples from the sciences, in astronomy, you have all these telescopes all over the world or in space, which are constantly collecting data. And you want to somehow extract what certain fundamental constants of the universe are from this data. Or maybe you have the genomes of a bunch of animals, and you want to figure out which pairs of animals have closely related common ancestors. Or maybe you see a disease spreading, and you know who came in contact with whom, and you want to figure out some properties of this virus, like how quickly it spreads. And in theory as well, people have come up with all kinds of different models to study high-dimensional inference tasks of different natures. And there's been a lot of work on each of these models. Perhaps some more recognizable ones might be the planet leak model or spike models or compressed sensing. Okay, so the main focus of the research direction that I will be telling you about today is, when does a high-dimensional statistical problem admit an efficient algorithm? So this is a fairly broad question and has been studied for several decades. And decades of research have revealed many broad algorithm design principles for statistical problems, like Markov chain techniques or convex programming and others. And my approach is to study the power and limitations of these general algorithmic techniques. And so far, my work has focused on Markov chains and convex programming. And in today's talk, I will focus specifically on the subclass of Markov chain Monte Carlo, or MCMC algorithms. So before I get into them, I want to spend a slide saying why we chose to study this particular class of algorithms over all the choices. So first of all, these methods are, in some sense, the go-to algorithm for statistical inference problems in practice. And they're really effective. They're really good at inference. They also run really fast. They tend to be fairly easy to implement. And they're also fairly versatile in the sense they can be adapted to new problems pretty easily. In fact, they're so versatile that they're also used well beyond the realm of inference, such as in optimization or integrating functions or simulating physical systems. All right, so now let's get into the slightly more technical portion of this talk. So the way this will be organized is I'll first tell you all some background on MCMC algorithms. MCMC is going to be my abbreviation for Markov chain Monte Carlo. And then I'll tell you all about some of the work that my collaborators and I have done in this direction, as well as some questions that I wish to work on in the future. Okay, so if you've not heard of Markov chain Monte Carlo algorithms, do not worry, because I will be building a lot of the background from ground up. So what is a Markov chain Monte Carlo algorithm? This is perhaps best illustrated via an example. So consider the goal where you were given one of these graphs from the block model, and you want to sample from the posterior distribution of the coloring given the graph. So here's a fairly natural algorithm that is often used for this purpose. So you start off by coloring the vertices randomly. This is going to have no correlation with the ground truth. You didn't look at the data in any way. Okay, but now you want to repeatedly perform certain simple local updates, which will hopefully actually improve how correlated you are with the hidden coloring. So in a single step, you choose a uniformly random vertex, such as the blue one that I've highlighted in green over here. You look at its neighbors. You see it has 3 red and 2 blue neighbors. And you recolor this vertex via some sort of noisy majority vote on its neighbors. So in this case, because you have more red neighbors, you recolor it with some bias towards being red. And in fact, it does seem like we recolored it red. And we simply let this procedure run for some time. So this particular process can be described as a Markov chain on the space of colorings of this graph. And one basic fact about this Markov chain is that as you let it run for time going to infinity, the distribution it converges to is actually the posterior distribution over colorings given the graph. And as you can see, we let this run, and it indeed seemed to have found a pretty decent coloring. And the term that we're going to use to refer to the long-term distribution of Markov chain is its stationary distribution. Okay, so now let me tell you all more generally what the Markov chain Monte Carlo paradigm is. So in general, your goal is to sample from some distribution mu. So you first start off by designing a Markov chain whose stationary distribution is this target distribution mu. And the algorithm is simply run the Markov chain for some number of steps and output the state that you finally ended up at. And as time goes to infinity, you do end up at a state which is distributed according to mu, which you want to sample from. Okay, but we don't have time equals infinity. We want polynomial and n-time algorithms. So the natural goal that this leads us to is to prove that when you run your Markov chain for polynomial and n-time, then the output is distributed according to mu. And this is a property of a Markov chain that we will refer to as fast mixing. Okay, so if we can prove fast mixing for a Markov chain that came up for us in the context of inference, then we get an efficient sampling algorithm. And if we had an efficient sampling algorithm for distributions such as the posterior, then it would give us an efficient inference algorithm. So okay, let's see what we can say about fast mixing. So the analysis of fast mixing of Markov chains is a decades-old study across the areas of theoretical computer science, probability theory, geometry. And there have been many books, monographs, and PhD theses written on the subject. And over the years, there have also been many tools developed towards the goal of proving fast mixing of Markov chains. So this suggests to us that there's many ideas for us to try to prove that these Markov chains that show up in the context of inference mix fast. Seems rather comforting, right? Okay, but there's a crack in this picture. Actually, it turns out that a lot of Markov chains that show up in the context of statistical inference actually mix pretty slowly. And just to give you a cartoon illustration, the kinds of distributions for which we know that a Markov chain mixes fast tend to have rather simple structure, such as the cartoon that I've depicted on the left. But the probability densities that you want to sample from in the context of inference problems tend to look rather insane, such as the cartoon on the right. But more concretely, this Markov chain that I showed you all a few slides ago for trying to find a hidden coloring in the block model actually takes exponential and n time to mix. Yeah.
Should I think of your cartoon as log concave measures or its distributions?
Sure. I think that's a good model to have in mind. Yeah.
Is it a rigorous result or just intuition?
The exponential and n time, this is rigorous. Yeah.
Okay, so going on Madhur's question, since I was itching to ask this before, but in this case, how should I think of a difference in optimization and sampling here? I mean, you're emphasizing the sampling, but in this case, I can just also optimize, and which would maybe even be better inference here.
Right.
Why are we focusing on? Can you motivate a bit why we're
why sampling? Right.
Really, what you want to do is optimization, actually.
Right. So actually, for this, so here's like an interesting feature of this stochastic block model. There is a regime of probabilities I can choose for generating these stochastic block models, where actually the number of edges in the planted partition is more than the size of the minimum bisection, even in a random graph which has no signal. So really, you do want to be using Bayes' rule. So in some sense, the min bisection may produce a cut which is completely uncorrelated with the ground truth cut. And this is in a low signal noise ratio regime where we do have other algorithms to recover this hidden partition. Okay, sorry, I think that was a mouthful, so let me say that again.
I mean, is this gonna come up later? The guy can wait, or is this because?
No, so maybe I do want to address it now, which was fine. Okay, so I can set up parameters for my block model so that, see, the planted cut cuts maybe 48% of the edges. But now if I look at the minimum bisection in the graph, then that maybe only cuts 40% of the edges. And further, the partition which cuts only 40% of the edges is basically uncorrelated with the planted structure.
Okay, so in the language of your model, you're saying that the map estimate, even if I had the posterior, taking the map estimate would result in a
Yeah, that's right. So the map estimate gives you something that's very deviant from typical
I really need
behavior.
to integrate here. So I really,
Right. So that's why I really want to use a Bayesian method.
but with but it drove from the posterior with hypermobility would be fine.
Yeah. No, that's a very good question.
Okay, but that's not captured by those figures. In those figures that you showed, it seems
Yeah, no, the pictures I showed in last slide were maybe meant to be more so a cartoon. Yeah, thanks for the question though. Okay, I'll keep going. Right, so we actually know that the Markov chain for this block model takes exponential and n time to mix. But I'm about to tell you something even more bleak. Actually, for many natural inference problems, and here examples of these natural inference problems are versions of the block model, but with more than two colors. The sampling problem is even computationally intractable under certain average case hardness assumptions. So this seems like demoralizing news. Does it mean that we should just give up and go home? Well, if you were to convey this news to a practitioner, they would just ignore you and run the Markov chain anyway. And in fact, for these seemingly hard inference problems, if you run the Markov chain on your laptop, you'll see that it still actually finds a good coloring, even though the sampling problem is hard. So what is happening? What is the mystery at play over here? Well, so it seems like this picture that we wrote earlier is not quite right. The Markov chain is giving you an efficient inference algorithm, but for reasons that don't go through efficient sampling. And in general, in the context of inference, rigorous guarantees for MCMC methods are fairly scarce. And my diagnosis of this is that it's because the approach to analyzing Markov chains in a traditional way are based on proving that Markov chain samples, and this approach fails. So just to make the kinds of guarantees we want to prove more concrete, in the context of inference, the kind of guarantee that we want to show is if you have data that's drawn from a natural probability distribution, and you run your Markov chain for polynomial n time from a random initialization, then you find a solution whose correlation with the hidden signal is high. And by high, I mean as high as what the correlation with the hidden signal would be if you got a sample from the posterior.
Correlation means simply Hamming distance in this case or something else. How do you measure correlation?
Yeah, so the Hamming distance. Okay, now let's contrast this with the kinds of guarantees that we are used to showing for worst case Markov chains. So typically, for worst case Markov chains, we say something like for any input, for any initialization you could have chosen for your Markov chain, and also for any test function, the average of that test function under the Markov chain distribution matches the true stationary distribution. So if you could establish the criteria on the left, then that's amazing because you do get all the things on the right for free. But actually, none of these things are true for a lot of Markov chains that arise in inference. So my research is geared towards trying to build a beyond worst case theory, which can actually hopefully capture the kind of behavior we want to see on the right. And what would facets of this beyond worst case theory for Markov chains look like? You'd want to say something about special inputs, such as those that come from natural distributions. You'd want to say something about nice initializations. And you also would like to only restrict your arguments to special test functions instead of all test functions. Okay, so now in the rest of the talk, I want to tell you all some progress that my collaborators and I have made in this direction, and certain questions that I wish to pursue. So in two distinct works, we gave frameworks to analyze the behavior of slow mixing Markov chains. And here by behavior, I mean how they behave on special test functions. And also a framework to analyze Markov chains from good initializations. And as a yardstick to actually say that these frameworks are doing something interesting, we were able to use the first framework to say something about this Markov chain that I showed you all a few slides ago for recovering communities in the stochastic block model. And we were able to, in this other work, we were able to make progress on some conjecture made in statistical physics. And I'll first focus on this application of the block model, which is based on joint work with my collaborators Kui Lu, Prasad Raghavendra, Amit Rajaraman, and David Liu. All right, so let's get into what we can say about the block model. So just to give you all a quick reminder, you have this graph with this two dense clusters with a sparse cut structure, and your goal was to recover this hidden clustering. And you want to do so better than random guessing. That's your yardstick of success. Yes, question?
So you mentioned that there is a rigorous lower bound of exponentially n for mixing time of this stochastic block model Markov chain. So then you have these three worst case criteria. So could you go over them? So was it over worst case distribution or was it for?
It was actually for the test functions.
Okay.
And I guess also the fact that the input is coming from a natural probability distribution as opposed to being worst case. No, but the key sticking point was that there are bad test functions. There are test functions for which the Markov chain distribution does not match the true stationary distribution.
Okay. But it was not worst case over distribution. It was from stochastic block.
Yes, that's right. Okay. So the stochastic block model has been very well studied over many decades, and there's a lot of literature on this. But today I'll only be focusing on one small slice of the story, which is maybe related to what we were able to do. So back in 2011, 4 people with a physics background, Bissell, Kurzakala, Moore, and Steberova, set out to precisely understand when you can actually beat random guessing to the stochastic block model and what the algorithms for doing so are. So in this non-rigorous work where their methodology was either experimental or based on physics heuristics, they were able to prove, they were able to verify experimentally that the Markov chain actually optimally recovers the hidden signal for the stochastic block model. And they also identified when it is possible to beat random guessing.
Sorry. I'm a bit confused here. When you say that MCMC optimally recovers the hidden signal, so you mean for the stationary distribution or after some polynomial time or some limited amount of mixing, and optimally over what? Because in some sense, if I just read it on face value, I mean, this is a tautology. You're saying MCMC samples from posterior, and the posterior is optimal, hence this is optimal, right? So I'm a bit like missing what the statement actually is.
Yeah. So, okay, let me disentangle this a little bit then. So, okay, if you were to get samples from the posterior, then you would have some correlation. Let's call that number like 70%. Okay, but now the Markov chain actually doesn't mix. It takes exponential n time to mix, but they run it for a time that's like basically linear in the number of vertices in the graph. And in linear time, they observe that it gets as good as the stationary. It does as well as the stationary would.
Meaning that the Hamming distance between what it finds and the truth is optimal.
Yes.
So basically you're saying that MCMC, linear time MCMC already behaves it has the same recovery as the posterior, and this is in all regimes or only in this regime where epsilon is, what is the optimal, what is the optimal with respect to here?
Right, okay. So I guess they, at least in their experiments, they tried it for like some discrete set of epsilons, maybe like 5 different values, but
the conjecture is that for all epsilon greater than this minimal threshold, it should.
Yes.
But this is not saying that this threshold is optimal. Like it might be still a regime in which I'm a bit confused about the.
Okay, yeah. So for the 2 community block model, okay. First of all, they say that you should only be able to beat random guessing when epsilon is larger than this, like 1 over root Pn.
Information theoretically.
Yeah, information theoretically, you should only be able to beat random guessing above this thing. And the second facet is when you can beat random guessing, I guess you can ask how much can you beat random guessing by? And they say MCMC is going to be optimal for how much you can beat random guessing by as well. Yeah.
So something you said, I think clarified things for me. I just want to make sure I'm thinking correctly. So the model is everybody gets a hidden coloring. So they get a hidden color. That's ground truth hidden away. Then the graph is created according to the P and the 1 plus epsilon times P and 1 minus epsilon times P. And that's what's revealed. Now, there is a well-defined kind of optimal thing to do, which is, so there's a theorem that says that actually sampling from the Bayesian, posterior is actually optimal in the sense of giving you the best expected, distance to the ground truth, which won't be 0 because you've lost information in going from the ground truth to this graph. So there's like a well-defined how close you could hope to get, maybe 70% close or whatever. If you were to do that, and there's a theorem that said that is actually optimal. It was not totally obvious to me, but I completely believe it. And then you're saying that, well, MCMC, while not actually sampling from that distribution, is nonetheless getting you as close as you could have hoped to get by sampling from the distribution.
Yeah. That's right.
But this holds like
linear in n.
But really want to understand results for every P and every epsilon.
That's a physics paper. They're showing it for some epsilon.
No. They're not. It's not just empirical. They also presumably have some arguments. But the claim, right? The conjecture is for every P and every epsilon. For every P and every epsilon, you will get if I do for posterior and you just run for linear time. You will actually get for every P and every epsilon, we'll get the same recovery. Whatever,
yes.
Irrespective of the threshold in the second, right? Epsilon doesn't have to be greater than 1 over square root.
Yeah, I guess if epsilon is smaller than that, then you can't beat 50%. So then the MCMC won't beat 50% either. Yeah. Thanks for the question. Yeah, that clarified things. Okay, so once they made this conjecture, there was a lot of work on designing algorithms that could beat random guessing in the entire parameter regime given by number 2. And people studied spectral algorithms, STPs, belief propagation, low degree polynomials, and such for this task. In particular, this conjecture attracted a lot of attention. But despite all this work, there was no result for the natural Markov chain. And now getting a result for the natural Markov chain isn't just a matter of presenting yet another algorithm. The Markov chain apparently runs fast. It's easy to implement. As you saw when I described the algorithm, it's something you could have implemented in like 6 or 7 lines of code. And it also has this added benefit of seemingly achieving optimal correlation. And maybe this is a more personal aesthetic thing, but I also find this to be the most natural algorithm for this problem. So we decided to study MCMC for the block model. And we were able to prove that it does, in fact, beat random guessing. And maybe not in the full regime where it's possible, but for some large constant factor above the optimal threshold. And this is the first non-trivial guarantee for the Markov chain for the stochastic block model. I would even go as far as to say that it's the first non-trivial guarantee I'm aware of for a slow mixing Markov chain succeeding at an inference task. Okay, so now I want to tell you all a little bit about some of the conceptual ideas that we introduced to prove this. But maybe I'll pause to see if there's questions. Yeah.
Yeah, so going back to the question first, so in this, in just to circle back to discussion, you're claiming that in this regime, that MCMC is provably succeeding. Just looking at the min-cut would provably fail. Is that understood correctly?
So actually, it's not in that regime. I do eventually hope to extend into that regime. So that's a good question, though.
So MCMC, of course, ran in polynomial time. But do you have something for linear time, or still it is polynomial, or what is the time for which you run MCMC?
Right. So I guess our running time is also n to the 4. So
okay.
There are definitely screws that can be tightened. So
no, that's fine. I was just making sure.
Yeah, I guess anyway, the way I see this is eventually the goal is to say something about Markov chains being optimal for a large class of inference problems, and these are maybe first steps towards building the theory for slow mixing Markov chains to articulate these things. Okay, so I'll tell you all about this conceptual idea of locally stationary distributions, which is something we study to analyze slow mixing Markov chains. So our approach to analyzing slow mixing Markov chains was inspired by optimization. So just to draw the parallel, if I give you some arbitrary function and ask you to find the global minimum of this function, it could be a hopelessly intractable question. There's many NP-hard questions that can be formulated as finding a global minimum. But if you wanted to find a point where the gradient is small, that is a local optimum or a first-order stationary point, then this is something you can always find in polynomial time, given some mild assumptions on the function. And your algorithm is to simply run gradient descent. Just go down, and you will eventually at some point hit one of these points of low gradient. Now, similarly, if I give you a Markov chain, sampling from its stationary distribution can be quite intractable. But is there some notion of a first-order stationary point in the context of sampling? And turns out there is, and we call this notion a locally stationary distribution. So to motivate the definition, let's start by making this plot where on the x-axis I have time, and on the y-axis I have the distance of my distribution at time t to the stationary distribution. And one basic fact about this plot is that it's always monotone decreasing, because running a single step of a Markov chain will always take you closer to the stationary distribution. Now, one fact about monotone decreasing curves, such as this one, is that you will always eventually hit a point where you're not decreasing at a rapid rate, where the derivative is small. And our insight is that actually the distributions you encountered on these plateau regions have useful structural properties that actually make them useful for inference. So just to give you all a more complete definition, I'm going to say that the distribution you have at time t is locally stationary if the derivative of your distance to the stationary distribution is small. And the appealing fact about this definition is that every Markov chain can be shown to hit a locally stationary distribution in polynomial n time when the state space is exponential in n. So while sampling from the stationary distribution could be hard, sampling from a locally stationary distribution is always computationally easy. I'll pause to see if people have questions. Yeah.
So I assume like if you measure the smallest by epsilon, it's fully n also depends on epsilon.
Yes. So here I guess the thing I'm calling small is like 1 over poly n. And okay, I guess the distance metric that we use is KL divergence. The exact choice of KL divergence is maybe like motivated by more technical reasons. Yeah, not.
Wait, a bit confused. Is this supposed to be tautologous because
it's supposed to be like it's not an interesting theorem.
Okay. This is like kind of obvious just because if you go down at some point you're gonna have to make a small step, right? I mean.
Yeah. There's nothing
here, right? Okay. Just making sure.
Right. I guess the interesting thing about this is maybe on the next slide.
Okay.
The distance you said that it is simply KL divergence. Does it take into account that there's a natural structure and you are also interested not only in statistical things, but these are distributions on binary strings? Does it take into account Hamming distance or not?
No, so it doesn't take into account the geometry of the state space as stated.
Would something like an analog of Wassermann distance would be better?
Right. So if you use a Wasserstein distance, then then it would in fact maybe have like state space considerations into account, and it will lead to a different non-equivalent definition, which could be useful for other things. That's a good question. Yeah.
So is there an analog of this in the functional world? Like, are you saying that the variance of certain, like there will be a point where the variance of functions will stop being
Yeah, correct.
It can also be interpreted in the function. When you apply functions to the Markov chain and like say the variance stops being.
Yes. Yeah, so you should really interpret these locally stationary distributions as ones where the variance doesn't decay when you apply like one more step. Okay. Right, so the key structural property of these distributions is something that I'll call the approximate equilibrium property. So what this says is, if you take a locally stationary distribution and you run a single step of the Markov chain from this locally stationary distribution, then you basically don't change the distribution at all. That is, the distribution before and the distribution after are really close in total variation. This is some quantitative analog of the fact that if you were at the stationary distribution and you ran one step of the Markov chain, then you remain at the stationary distribution. Oh, yeah.
You're not saying this always is the case. You're saying this is a property of something.
So this is a property of being a locally stationary distribution.
Just saying any local stationary distribution will satisfy this?
Yes.
You must be assuming something because I think you can construct. Are you assuming something here?
Right. So I guess I was assuming that you're locally stationary with respect to the KL divergence in particular. So I think if you use other metrics, then this ends up not quite being true.
Okay. Okay, I guess maybe why can't you go through a bunch of distributions which are all just completely have nothing to do with the?
Okay. I guess
they're very different from each other. I mean, it seems that you should be able to do that, right? I mean, if you're extremely close to being non-ergodic.
No, so right. I realized I didn't mention this. We assume the Markov chain is time reversible. So I think if you had a not reversible Markov chain, then you could go from one cluster to the next and cycle around. But because you're time reversible, you can't have acyclic, you can't have a directed graph-like behavior.
Even if you have time reversible, for example, it could be different in even and odd states and still be time reversible. You need some stronger.
Okay. Yeah, I guess another thing which is also maybe underspecified, the Markov chain is running in continuous time. So there's a Poisson clock that ticks every time. So now if you have a bipartite thing, you the mass diffuses that instead of these are good questions and okay. Okay, so a general recipe that our proofs follow is something that I'll call a proofs to algorithms principle for Markov chains. So I guess in the context of estimating the hidden coloring, let's say you happen to have a proof that the true stationary distribution does in fact estimate the hidden coloring well. If we can check that this particular proof uses only this approximate equilibrium property, that is, the distribution doesn't change much when you run a single step of the Markov chain, then for free, you also know that because the locally stationary distribution has this approximate equilibrium property, it estimates the hidden coloring. And in general, you could imagine applying this principle towards showing that the Markov chain satisfies any property you want of your choice, as long as you can get a proof using only this approximate equilibrium property of the Markov chain. And we'll be able to use this for an application beyond inference. And in particular, we'll be able to show that a Markov chain whose stationary distribution is the uniform distribution of independent sets in a graph finds a large independent set as long as the graph is triangle-free. And actually here the sampling problem is straight up NP hard, but you're still able to imitate one of the properties of this distribution, which is the size of the independent set.
You mean in the worst case or not? Because
so this is a worst case.
Worst case, yeah.
Yeah.
But it might not exist. Large independent sets.
So I'm assuming that the graph is triangle free, and I guess my benchmark for large is if you have a d-regular graph and you know it's triangle free, then you know that there's always an independent set of size n over d times log d. So I guess n over d is like the trivial bound, and you get an extra log d factor.
So you can improve over. So we'll talk about it.
So isn't there already a sampling proof for this n log d?
So there's a sampling proof which is based on analyzing what happens if you take a uniformly random independent set. And I guess the thing I'm saying is if you take this proof and go through it line by line, you'll see that it only really needs this, the distribution is approximately equilibrium. So you get it for the Markov chain distribution too.
Sorry, just one more question. Is there a way for you to detect when you have this station?
So there isn't, because I guess when you're running a Markov chain, you only see samples, right? So, but the way to guarantee that you sample from a locally stationary distribution is to pick a random time between 0 and t, and run it for that amount of time. So like the mixture distribution over all times is locally stationary. Okay, so I told you all about locally stationary distributions as a framework for analyzing slow mixing Markov chains. Now I want to switch gears and tell you all a little bit about how to analyze Markov chains from good initializations, as well as an application to a certain problem from physics. So just to tell you all a cartoon of the issue that we're trying to handle over here is maybe you have a Markov chain and in your state space, you have some small pocket which only has junk solutions that you don't want. But if your Markov chain somehow ends up in that pocket, you're simply trapped there. And this is a phenomenon that shows up for very simple inference problems, such as random constraint satisfaction problems or variants of the stochastic block model. Now, the empirical take to handle this sort of an issue is to either use a random initialization or try to choose your initialization more cleverly, such as in this way called simulator annealing, which I will tell you about and maybe hopefully tell you a theorem about as well. So annealing is this 40-year-old heuristic. It was introduced for solving combinatorial optimization problems. And some of the early stat solvers also use this algorithm. And some version of this algorithm is also adapted for some of these generative models that I'm sure a lot of you are familiar with. And now just to tell you a little bit about what the annealing algorithm is. So the premise is you want a sample from some distribution that looks kind of wild. And the way you actually approach the sampling problem is you design some other distribution, which is way easier to sample from that easy distribution. And now you construct a path of distributions between this easy to sample from distribution and the distribution you want to sample from. And now you feed in a sample from the first distribution to a Markov chain which tries to sample from the second, feeding the output of that Markov chain to the third, and so on, until you actually have a sample from this distribution on the right that you care about sampling from. So in general, as far as theoretical analyses of annealing go, there have been like several situations where one has been able to analyze annealing for some problem using problem-specific structure. But there's no unified framework for doing so. So with my collaborators, Bryce Huang, Amit Rajaraman, and David Wu, we gave this unified framework to try to show mixing of Markov chains from good initialization, and in particular, to say something about annealing. And as a yardstick to say that a framework is useful, we were able to use it to make progress on a conjecture from physics, which I'll hopefully tell you about briefly now. Okay, so let me tell you all about a certain model from statistical physics called the spherical spin glass. So this model was introduced by Gross and Mazard in 1984 as some sort of stylized model to study magnetic phenomena. So in this model, you should think of there as being some energy function h and some other parameter beta. And this model is a probability distribution on the unit sphere, which is proportional to e to the power beta times h. And in the spherical spin glass model in particular, this energy function h is chosen to be a random polynomial. That is, a polynomial, all of whose coefficients are drawn independently from some nice probability distribution. Okay, so now why do physicists care about this model or running a Markov chain for this model? Well, it's because if they can understand the behavior of the Markov chain as you change this beta parameter, then it actually tells them something about how properties of magnets change as you change their physical temperature. Okay, so motivated by this, three physicists, Crisanti, Horner, and Sommers, conjectured how the model should behave. And they identified these different phases. One phase where the Markov chain should mix from anywhere from a worst case initialization, but also a second phase where the Markov chain does not mix from a worst case initialization, such as if you initialize in one of those small red bubbles, but instead would still mix if you gave it a good initialization, like a random initialization. And once they made a series of conjectures for this model, there was a lot of follow-up work on trying to prove these conjectures from the mathematical physics and probability theory communities. However, despite a lot of work, many existing results for the Markov chain hit this uniqueness barrier. They could not get past the first threshold. I would say it's because the techniques employed either established that you mixed from worst case initialization or didn't establish anything. So this was a good test bed for something that we called a framework for analyzing mixing from good initializations. And we were able to show that, in fact, you can break past this uniqueness threshold and prove that the annealed Markov chain samples in that entire regime. Okay, so that's it for the technical portion of the talk. I want to spend the next, say, 5 minutes or so telling you all about some directions that I'm interested in pursuing in the future. Okay, so just to give a recap, there seems to be a budding beyond worst case theory, where maybe you're able to say something about Markov chains on special tests instead of all tests, or Markov chains from good initializations, or prove guarantees for them for inputs that come from natural probability distributions, as opposed to worst case inputs. And the directions that I'll mention are going to be geared towards building up various facets of this theory to a greater level of maturity. Okay, so let me tell you all what my overall dream goal for Markov chains and statistical inference is to prove a classification theorem, to prove that MCMC is a universal algorithm for inference. Now, what would such a theorem or statement look like? So let's say tomorrow we encounter a new inference problem in the wild. I would like there to be a simple mechanical procedure, by which I mean a simple procedure that us as computer scientists or mathematicians can carry out on a piece of paper and pen. And now once we carry out this procedure, it should tell us one of two things. It should either tell us that the inference problem is easy, and then the theorem should tell us that it's easy because you could have done the Markov chain and it's an optimal algorithm. Or this procedure tells us that the problem is hard, and the theorem should tell us that a lot of commonly used algorithmic techniques fail. And this is inspired by certain analogous theorems that are known in classical complexity, such as the dichotomy theorem for CSPs or the uniqueness conjecture. Okay, and for inference, this is not a pipe dream, because actually such candidates for the simple mechanical procedure do exist in the literature. And in particular, these candidates seem to produce predictions that are consistent with our beliefs for a large bag of example problems. So answering this question is a matter of relating what these candidate heuristics are telling us with what the Markov chain is actually doing. And doing so would hopefully along the way also resolve certain well-known open questions in this area of statistical inference and analyzing Markov chains for inference. Now there's a similar meta theorem to be proved, which I won't go over in the interest of time, but basically it's some sort of meta theorem to try to say something about when a Markov chain mixes from a good initialization. The final slide that I want to spend a little bit of time on is to tell you all about certain directions that I'm interested in the context of analyzing Markov chains outside of inference, such as in optimization or coding theory of physical systems. A particular one that I find intriguing actually is this example from physics. So here's a documented phenomenon that we don't yet have a good understanding of. Sometimes if you take a glass of water, and which is a room temperature, and a glass of water that's slightly heated up, the warmer water sometimes actually freezes first if you put both them in the freezer at the same time. And why would Markov chains have anything to say about this? Well, it's because the freezing dynamics of water are governed by some sort of local Markov chain. And okay, it's more so I find this phenomenon fascinating, and maybe it'd be nice if the beyond worst case lens could say something about this problem. Okay, finally, I want to spend a slide just highlighting some of my other interests. Over the past 7 years or so, I've been really interested in spectral graph theory, and in particular in problems related to constructing expander graphs, which are these objects that are relevant in pseudo-randomness and coding theory, and also in other sub-areas of theoretical computer science. I've also spent a bunch of time thinking about random graphs. And finally, I've thought about semi-definite programming and how good semi-definite programs are at inference problems. Okay, and finally, I want to end this talk by giving a shout out to all my collaborators from whom I've learned a lot.
Time for maybe a couple of quick questions.
Yes.
So then that I'm trying to understand the annealing result. So in that case, can you actually prove that annealing the MCMC with annealing will mix or will recover something when MCMC without annealing provably fails, or what?
Right. So let me just go back to the slide. So there's this particular regime of this inverse temperature beta where MCMC from a worst case initialization provably fails the sample.
Worst case meaning also from random, I assume.
No, actually, by worst case I really mean contrived. Like you look at the input and then you as the devil decide where to initialize.
I see. But from a random initialization?
From a random initialization, we believe that it should work, but we don't know how to prove it, so we prove something for annealing.
Yes. But annealing is from any initialization or from random?
So annealing, you start off at random and then you like slowly work your way out.
I see.
Yeah.
So at least you can say that you need one step of annealing in some strange sense.
Right. I guess.
Okay.
Like random is like one step of annealing, whereas we had to use a path.
Okay.
So I guess this was more a matter of like trying to break past like the worst case barrier.
Excellent.
Other questions?
For SBM models, your current proof analysis is using these locally stationary distributions. My question is why this approach fails in some parameter regime and only work for some parameter regime?
Okay. So actually, the deficiency is not in the locally stationary distributions framework itself. One thing we need to plug into this framework, if you will, is some result on fast mixing for certain models where your data is pure noise. And over there, we don't understand the sharp phase transitions yet for when mixing is possible and when mixing is not possible as you change like some temperature like parameter. So I think once we can get a sharp mixing result for these pure noise models, then it actually would translate to an optimal recovery algorithm under this locally stationary framework.
So you mean we will not get to the local stationary distribution for this region?
No, so you do always reach a locally stationary distribution. The question is, when is a locally stationary distribution actually giving you a good right? And to prove it, there's like something that needs to be proved for actually models that are not too different than this, like a spin-last thing. Like, in fact, the reason we start thinking about these spin-last models is so we could tighten those results.
Okay, thank you.
Yeah.